In this video, we're going to look at an alternative method for finding the general term of quadratic sequences. We're going to look at 3 examples, and in all of them we're going to use this slightly different method. There is one thing we need to remember from the other method that we looked at, and that is that when we find the second difference for a quadratic sequence, this is always equal to double the number multiplying the n squared in the general term. We will have a look at that again as we go through these examples. So let's have a look at the first example. Here we have 4, 9, 18, 31, 48 and 69. The first thing we have to do is still look at the differences. So 5 is the first difference, 9, 13, 17 and 21, and then we must look at the second differences, and we see they are 4, 4, 4 and 4. This is to confirm that we are indeed looking at a quadratic sequence because the second differences are the same, and also we need this value here. Once we have that value, we know that the first part of our general term is going to be 2n squared. It's always half the number of the second difference. So the second difference is 4, so we have 2n squared. And we make use of that in the next step. So I'm just going to copy the sequence down here, so we've got another copy of it. And that is equal to the sequence. But what we're going to do is underneath that we're going to write 2n squared. So here we have un, and underneath it I'm going to write 2n squared. That sequence. And that sequence is 2 times 1 squared is 2, 2 times 2 squared is 8, 2 times 3 squared is 18, 2 times 4 squared is 32, 2 times 5 squared is 50, and 2 times 6 squared is 72. And once we've done that, we're going to do a subtraction. We're going to subtract the 2n squared from our sequence. And what we do there is we remove the n squared part of the sequence. So 4 minus 2 is equal to 2. 9 minus 8 is 1. 18 minus 18 is 0. 31 minus 32 is minus 1. 48 minus 50 is minus 2. And 69 minus 72 is minus 3. Now we treat this part as a sequence in its own right. And looking at this one, we look at the differences and we get it's minus 1, minus 1, minus 1, minus 1, minus 1. So the orange sequence is a linear sequence going down in minus 1. And we know how to deal with that. We have a linear now which goes down in minus 1. So the nth term of that is minus n. And then to get from minus 1 to 2, we have to add 3. So the linear term is minus n plus 3. And this gives us our final answer. Our final answer here for the original sequence is what we get when we combine the red 2n squared with the purple minus n plus 3. So our final answer for the general term of this sequence is 2n squared minus n plus 3. And that gives us the terms. If we put in n equals 1, we get 2 times 1 squared is 2, minus 1 is 1, plus 3 is 4, is indeed the first term. 2n squared when n is 2 is 2 times 2 squared, so 2 times 4, which is 8, minus 2, which is 6, plus 3, which is indeed 9. And if we carried on going, we'd get all the other terms of this sequence. So un equals 2n squared minus n plus 3 is indeed the correct general term. Okay, let's have a quick look at two more examples of this. Here we have another sequence, 2, 0, 0, 2, 6. First of all, we find the first differences, minus 2, 0, 2, and 4. And then the second differences are 2, 2, and 2. So this time, the second difference is 2. So we know we have an n squared, a 1n squared, because the coefficient of the n squared, the number multiplying the n squared, is half of 2. And then we use this sequence again, the original sequence, and that is un. And underneath it, this time we're going to write n squared, which is 1, 4, not 6, 1, 4, 9, 16, and 25. And then we do the subtraction. We subtract n squared from un. 2 minus 1 is 1. 0 minus 4 is minus 4. 0 minus 9 is minus 9. 2 minus 16 is minus 14. And 6 minus 25 is minus 19. We then look at the difference of these, which is minus 5, minus 5, minus 5, minus 5. So we have a linear sequence remaining, which is minus 5n, because the first difference of the linear sequence was minus 5. And then to get from minus 5 to 1, we have to add 6. And then once we've got that, we combine the two bits to get our final un equals, well, it's this bit up here, n squared, plus this bit here, which is minus 5n plus 6, giving us our final answer for this sequence, n squared minus 5n plus 6. The third and final example is this sequence, minus 5, 4, 19, 40, and 67. Once again, we start by looking at the first difference of the sequence, 9, 15, 21, 27, and then the second difference, which is 6, 6, and 6. This tells us that we have a 3n squared in our general term. So we're going to take away a 3n squared from the original sequence. So once again, we have un, and we're going to take away a 3n squared. So we have a 3n squared, and 3n squared is equal to 3, and 3 times 4 is 12, 3 times 9 is 27, 3 times 16 is 48, and 3 times 25 is 75. We now do a subtraction. We subtract the 3n squared away, and we get minus 8, minus 8, minus 8, minus 8, and minus 8. So this time we have a constant sequence of minus 8. So we can combine them, the 3n squared, so we get un equals 3n squared, and the constant term minus 8. So that is an alternative method for finding the general term of a quadratic sequence. We find the second difference and use the fact that we know the first coefficient of n squared will be half of the second difference, and then we subtract that sequence from the quadratic sequence, removing the quadratic part from our sequence. We then find a linear sequence and combine this with the quadratic part that we subtracted previously.